Okay, so that is steady bifurcation. Now, we can look for other kinds of bifurcation. In particular, we can look for Hopf bifurcation. Hopf bifurcation occurs when, not when the eigenvalue goes through 0, but when the real part of a complex pair goes through 0. So let's write that down. By doing what we just did, we have completely solved the question of stability of the basic state. That is to say, if we plot the basic state, yeah, in fact, it's already here. Here it is. We have this, and this we did by looking at the Jacobian, but then we did more than just look at the Jacobian. We also found that there were new branches that were the positive and negative branch. This is what we just did. Okay, but there's nothing more to be learned about the trivial branch. We found all of its bifurcations because we found its eigenvalues, and we knew that they were either all negative or that one of them was positive. We knew what they were. They're not complex. Okay, excuse me. Yes, of the trivial state. However, now we can do linear stability. I told you that linear stability analysis is a property of what you're doing it about. You linearize about something. So now that we have these new solutions, and we don't just have them, we have their analytic form. They're right there over here. We have their form, and we have the Jacobian in general. We have the Jacobian in general for any x, y, z. We have new solutions. We can evaluate this Jacobian not just at 0, we can evaluate it at the new solution. So here we are going to do that. This is the Jacobian evaluated at the new solution. Okay, so here it is. You recall that we had minus sigma 0 in the first row, and then we had a z in that last row of the Jacobian, a minus x here. We had a minus z here. So we put that in here, z. Oops. Okay, and here's the x and the y, or rather this was y, this was x, and this was what? Did I make a mistake? I should have a z. Oh, r minus z. Okay, it was over here. R minus z, and so r minus z is 1. Okay, that's why there's no z. Okay. So this is the Jacobian for the evaluated at the new solution. And now to find its eigenvalues, you can write out the whole cubic formula, and this is usually what people do faced with this problem. And then they go, oh, what do I do now? I don't know how to solve cubic equations. And I hope that when I wrote the problem, I hope I included the hint to assume, just as it was very much easier to find out where the eigenvalues were 0 when we went back here, instead of, I said, let's not just find the eigenvalues, let's set the eigenvalues to 0, and that'll turn out to be really easy, rather than getting a formula for the eigenvalues and then setting it equal to 0. Let's just right away set it to 0. So too here, we are not looking for the eigenvalues in general. We're not looking for solutions to this whole cubic equation. We are looking to see when we have a Hopf bifurcation. And at the Hopf bifurcation, lambda is equal to I omega. And hence, odd powers of lambda have I in them. Even powers do not. And this single cubic equation decouples into 2 equations, one for the real part and one for the imaginary part, and it all becomes much easier. You're not finding all the eigenvalues for all values. You're finding an equation satisfied when lambda is equal to I omega. So writing over this equation and this equation here, setting up the imaginary parts equal and the real parts equal, turns out to give you easy arithmetic. Here are the 2 equations to be satisfied. So you can see that you have 2 expressions for omega squared here, because you just divide through by omega here. So you have two expressions for omega squared, and between the 2 of them, that allows you to relate these quantities, b and sigma and r. So you see here we are doing it. We've just written 2b sigma r minus 1 is equal to sigma plus b plus 1 times r plus sigma. We've just multiplied out. And now we have r that occurs here and here. right? So we just have an equation for R, where we're going to put sigma plus B plus 1, plus 2B sigma. And the plus 2B sigma is going to be combined with this 1 here to give us 3, right? And so we get a value, and that value is 24.74. For the particular values, recall that B, that's a geometric factor of 8/3, and sigma, that was the Prandtl number for water, which was 10. So this is a famous value. This is the value at which the Lorentz model undergoes a Hopf bifurcation. Okay, so we drew this, and now we have something else to draw. This took place, this is the R axis here, and this took place at R equal 1, and that was a pitchfork. And over here, at the value, it's not at all drawn to scale, R equals 24.74, we have a Hopf bifurcation. We have loss of stability here. But as before, we've only done linear stability analysis. We know that it's going to leave, but we don't know where it's going to go. And we also know in what way it's going to leave. It's going to leave in a complex way, a spiraling way, because that eigenvalue has its real part is changing sign. The real part tells you, okay, you have here that you had a point that was a stable spiral, and after the bifurcation, you have an unstable spiral. Okay. So you're leaving this, but where are you going? And that part we can no longer do in this easy analytic way. It turns out that that Hopf bifurcation is subcritical. And what does subcritical mean? In this, you recall that it means that the limit cycle is not to be found to the right, but to the left. And now what does right and left mean in this context? It means the direction in which the eigenvalue that's going to become unstable is increasing. So if we go back, let's go back to yesterday's class. Do I still have it up someplace? Yes, here it is. Come on, there, okay. Now we'll go here. Yes, so in the supercritical case, we had a situation before with a stable spiral going to an unstable spiral, and it's in this, it's where the original node, spiral node, was, it becomes unstable that the new limit cycle exists. This is the supercritical case. You see here it's unstable, and you've surrounded the now unstable point by a stable limit cycle. The subcritical case, it's the opposite. That is to say, it doesn't matter whether you're talking about left or right. The point is that it is where the spiral node is stable that the limit cycle exists. You have here you have an unstable node surrounded by a stable limit cycle, whereas in this case you have a stable node surrounded by an unstable limit cycle. And here it's drawn in that direction, this left-right thing, but it doesn't matter which one you call increasing mu. We can just flip this picture. Oh, excuse me, no, but that's not what we want to do. Sorry. We want to stick with this picture. Excuse me, sorry. We want to stick with this picture because what we have just done is a calculation that says, we haven't done a calculation of the limit cycle. That we don't know how to do. But we've done a calculation of the black and white point. We've said that it has eigenvalues with a negative real part here, meaning you're going in, and here it's going out. It's positive real part. It's got an imaginary part which sends you round and round, but it sends you outwards here and inwards here. And that is the case for this as well. If you look really close, you have the same situation here for those fixed points. You're going from a stable spiral to an unstable spiral. The difference is where is the new limit cycle. And in this subcritical case, it exists where the original point is stable. So you are creating a limit cycle like this. That doesn't mean you're not spiraling out here. You are spiraling out here. But I'm not telling you where you're going. I don't know where you're going. Here I know that to the left, I mean, I don't know it by any means that I've told you about, but it's known that this limit cycle that is created at this bifurcation point exists where the state is stable. And of course, a lot is known about the Lorentz model because it's such a classic system. So we can go into what is known. Oh, now let's get out of here. Go back to the other class. Okay, so this is a picture that is studied, and this limit cycle here exists up until 13.926, and well, you can and the subcritical bifurcation, alpha bifurcation, we said, is 24.74. And let's maybe look at some of these values, see what happens, if I can still get that demonstration up. Before doing that, let me go through here, look at all these values, 13, 24, 30, up all the way to 214. Let me, before looking more at the Lorentz model, let's recall that we derived the Lorentz model by starting with these equations of convection and all the approximations that we went through. You remember that we, of course, there was free slip and all this, but in particular, we assumed these two-dimensional rolls, and then we put in the eigenfunction, so we neglected the 3 pi z. All of those assumptions kind of okay at the threshold, but they're really less and less okay as you go on. They're not even very good by the time you get to r equal 2. And so the idea of looking at this up to r equal 214 has no relation whatsoever to convection anymore. This just becomes an object that you're studying in its own right because it's become famous as the prototype of deterministic chaos. And probably some of you know already the story of what happened. Lorentz, actually, he was a meteorologist. He really was interested in convection. He really did want to study convection. He made this model, and he didn't have in mind discovering chaos and finding, go to up to r equal 214 and so on. He wanted to know about the ocean and the atmosphere. Anyway, so he ran his model, and then his program, for a certain amount of time, his program stopped because he'd only run for a certain amount of time, and then he restarted. No, I think there must have been two things. Yeah, he must have kept going, that's right, but he had a restart file, and so he also ran a case with the restart. And he found that the one with the restart was different than the one where he just kept going. So of course, he thought he had a bug, and of course, most likely he would have had a bug. Everybody knows if you get different results, almost surely you have a bug. But he did whatever was necessary to know. And the answer was that he had, when he did his restart, he did it from a certain, he kept 5 digits, say, of the solution. So when he was doing it, when he was doing his continual simulation, he had however many digits he was computing with, maybe 8. But with his restart, he was starting with 5 digits. So he was starting with a slightly different initial condition. And this is how Lorentz discovered sensitivity to initial conditions, is when he started from the truncated restart file, it was different from just continuing, where he had a different number of digits. So this thing about how it goes, it does this and then does that, and then that depends on those last digits. And the problem with weather prediction and all those kind of things, I mean, we can go back to atmosphere, is that to get another day of accuracy, you need another digit and another digit of precision in all in all of the properties of all the markers, and you can never, if you got 10 more digits, you would get 10 more days. You would never, I don't even think it's that, it must be less, I think it goes logarithmically or something, but you can never do weather prediction that way for a month, because you would need more digits than you can ever hope to get. Anyway, so let's go back then to what I said, if I can get the simulation working, let's try and do that. Let's keep in mind some of these values. Let's, yeah, let's go in the 24.3 range. Let's see if we can do that.
Sorry, what's the strange attractor?
Yeah, what's a strange attractor, right. I wish I knew more about this. Yeah, a strange, okay. Before all this, it was thought, and those who know about theoretical dynamics can know maybe more about the history of things. You know, we talked about fixed points, and we talked about limit cycles, and then there's another object, you know, this tori. If limit cycle undergoes another bifurcation, you go around a torus, and there's even other higher dimensions and so on. You know, but all these have regular properties. But the idea of a bounded set on which you don't leave, but where you have this sensitivity to initial conditions, this was, I believe, a new one that was discovered in the 1960s, and that's what a strange attractor is. It's a bounded set on which all trajectories converge, but within which your trajectories can go every which way. It is neither a fixed point where everything goes to that point, nor a limit cycle where everything converges to that limit cycle, nor a torus where everything, you converge to it, this set, but your motion on that set is chaotic. Okay, anybody with more? This is not my strong point.
Right. If
Yes,
I can add a
please do.
historical note, around 1890, Poincaré did a bunch of celestial mechanics, three-body problem kind of stuff, and showed that there could be chaotic things that have this kind of behavior. So in some sense, like a lot of this stuff is discovered because of Lorentz, but there is, you know, earlier precursors and such.
But I will ask you a question. What Poincaré did with celestial mechanics, that was all conservative systems, not dissipative ones, right? Whereas, so there is no idea of contraction, and so wasn't Lorentz, so there wasn't an idea of an attractor, since there's conservation of volume, and so wasn't the chaos that Poincaré was talking about more like the Hamiltonian chaos sort of thing?
Yeah, I guess it was in a Hamiltonian setting. But his arguments wouldn't work even if you sort of went beyond the Hamiltonian.
Went beyond the Hamiltonian setting.
Yeah, I'm not sure what he actually did.
You think they might well have applied to a situation where you have an attractor? As well, perhaps, yeah. Okay, just as, okay, everybody likes dualities, right? So there's, you know, say, in fluid mechanics, you can have laminar and turbulent. Say, I don't really like that because in between you have other things. Or you can have incompressible and compressible, right? That's a big dichotomy. Or you have Newtonian and non-Newtonian. Well, in dynamical systems, one of the big dichotomies is between dissipative and conservative. I think there's gradations between that, but let's say more or less. Okay, my specialty, because I do sort of lowish Reynolds numbers, Navier-Stokes, is dissipative. Hence this word attractor. Attractor means that volumes of phase space get smashed down. You go to an attracting point, or you go to a limit cycle, and your volumes are not conserved. There's a whole other species of dynamical systems that has equal importance and is studied in general quite different ways concerning conservative. And conservative means volumes are conservative, or conserved. So you would not smash down to a point. You would stay, whatever your volumes are, they would be conserved. And so this word strange attractor, I mean, the idea was supposed to be the dissipative stuff. Since you were decreasing, you were kind of reducing the chaos. You're going down to something that's kind of simple. But so the strange and attractor are kind of supposed to be vaguely contradictory terms, because the attractor should bring you down to something that, you know, from then on you're all just kind of plain vanilla. But strange, that you're leaving. So the idea is you're smashed down, but within your smashed down surface, you are going for that butterfly thing from the Lorentz. You go to that. You're not someplace else. You get smashed down to the butterfly. But then when you're within the butterfly, you might be going right or left in kind of chaotic way. Would you sort of agree with?
Yeah, I mean, like in the pure side of dynamical systems, there's no definition of a strange attractor.
No definition of strange attractor.
People don't.
So this is like the other thing. So it's a good thing I never learned this properly. There is no proper definition. Yes, so I'm not missing it. Good. Okay.
Just like chaotic. Chaotic. There's no textbook that, well, some will, but in the field, there's no there's not a like standard thing of like this system is chaotic or
I'm
not.
saved, I'm saved. I'm not ignorant, I'm ahead of my time. Okay, so let's see if we can get this demonstration going again and watch what we'd like to do. But see, said since it's all, no, it's okay. We'd like to go to a value, the 28 is a classic value at which it is chaotic. Let's go to something more like 24.5, and let's see, although I bet I'm not going to be able to start to, let's see what happens here. You notice those two wings here, they are each about one of those two fixed points. This center here, this one here, that's one of the fixed points, and this is the other fixed point. Okay, and the fact that you go round and round, of course, has to do with the fact that we just found this hop bifurcation, this going roundy sort of thing. Let's make it go faster. Can we do that? Yeah. There. So that's this really sensitive area here where it decides which way to go. Sometimes it keeps going several times around, and now it's switched.
So I may have missed something. Physically, what is happening?
Yes, right. In fact, not much is happening. What are these things? They're rolls that we're doing this. The geometry is not changing. All this are coefficients of the psi, T1, and T2 functions. So the function, the appearance is the same. You have these two convection rolls. But sometimes you're doing this, and sometimes you're doing this. And that is what you're doing. That's what that alternation is here.
Cool.
You're alternating between doing this and doing that.
And so that will change.
Yeah.
So that'll
That's right.
change.
You do
without
this,
disturbing the
this,
system.
this a bunch of times, and at different speeds, because okay, the one where you're just doing this at constant speed, that is a guy that exists right here in the center. That's a fixed, something that's now become an unstable fixed point over here. And this one here is the one that does this at the same speed. The fact that you're spiraling around, it's very, this is a French word, trompeur, is John Chang here.
Misleading?
Yeah, misleading, that's right, yeah, that's good, yeah, good translation, right. You see, that's to say, here too, you have something that looks like two roundy things. But that's not what that means, even though it looks the same in the picture. It looks at these two butterfly wings look like convection going like that. But when I do this with my hands, I'm talking about particles and what they're doing in XZ space. This is, and this is also called XZ space, but that has nothing to do with the geometric XZ space. This X and Z are coefficients of temperature and velocity functions. This X positive means that you have rolls that are going around in this sense, and this X negative means you have rolls that are going around in that sense. So a real notational nightmare here. This XZ does not mean, these loopy things are not the particles that are going around.
Fixed Q and K here.
You fix Q and K,
Okay,
that's right.
the
So
rolls
you're
are
always,
the same.
that picture, the picture of the convection is the same. You're not allowing it to do anything other than this. Indeed, we still have that aspect ratio, that 1.4 that came from the free slip boundary conditions, and this is what it looks like. What's changing is these arrows. The arrows show the directionality, hence, which is decided by the positive or negative X, because X multiplies psi, which is the stream function, and stream function being positive is counterclockwise and negative B is clockwise, whatever. And also those arrows could be, if I had used them that way, showing the magnitude of the speed, how fast your guy is going. And so for big X here, when you're at a point here, your particle is doing this, and when you're at a small x here, your particle is doing this. Which is natural. You could not possibly go from having your particles do this to all of a sudden decide to do that. Obviously, if they're doing this, they're going to kind of slow down and then eventually do that. So this is the magnitude and the sign of this motion. Okay, but I'm glad you asked that question. What is happening is qualitatively, phenomenologically, not interesting. There is no spatial dynamics here. It's complete, the picture looks just like that red picture.
This traces out our change in temperature and velocity for particles moving in these rolls. Is what the say the graph.
That's right. It's changes in, yes, this has to do with the velocity,
Yeah.
and this has to do with the temperature. In fact, this particular viewpoint of it, the Z, has to do with that temperature function you were talking about, that one that does not vary in X. That's just the fact that you're hotter here and colder here. Okay, but yes, this is a tricky, the fact that you have here this picture that's like this with an X and a Z here, but that has nothing to do with that picture there, where you also have a thing that looks like that with an X and a Z. One of them is phase space, and the other one is particles.
So if you've got two rolls,
Yes.
are they coupled together? So are they always going the same velocity, same temperature, whatever? Or I think you said before that we could have roll A going at one speed, roll
No,
B going at
no, they are coupled together. That functional form has been given, and it is, that functional form, it does not, it's purely trigonometric dependence in this horizontal direction. It's a sine q at, one of them is as positive here as it is negative here. The only thing that changes is how fast or how slow it is.
Yeah.
Spatially, it's completely uninteresting. There's no variation in X that's not in that original formula, which is that psi is sine qx times a sine pi z. It is merely the coefficient in front. Okay, I was hoping here to find some of this metastable thing, but you see it's still going around. Okay, still being chaotic. Let's see if we can find something a little bit. We're going to be finished in just a moment. Let's see if we can start with something. I guess we need to start with something. Start with 25. I'm wondering if we can possibly go just to one of those stable, one of those steady states. Because remember, it's stable here. 24.2 is below 24.74. So this is here, at this place here. It should be possible to, if you're sufficiently close, to just go to that. It's not very stable, but it is a little bit stable. So hopefully, eventually, it will get to the center and maybe just stay there. I think it will. Notice the parameter values are the same. I only tried to choose an initial condition that was close enough to the, we'll see. Okay, so let me just keep it going, and let me finish the class here. It looks as though there's a lot more to go, 39 slides, but there isn't, because the rest is qualitative.